welcome back. So he's very much, of course, service. So today, anyway, he's going to speak on best proximity point results and developments and some recent result in this direction. So I welcome Professor Chaudhary Sahab to deliver his talk on this particular research area of the fixed point theory.
Thank you very much. Oh. Good morning, everybody. Let me begin by extending my heartiest thanks to the organizers for their invitation, in particular to Professor Javed Ali, who personally extended the invitation to me. And I hope that all of you have enjoyed the previous lectures, all of which were related to fixed point. Now, the point is that the name suggests that something different from fixed point, which is the best proximity point. And if you are not really acquainted with this phrase, then a very natural question will come to your mind that this is a workshop for fixed point theory, and how can a topic, a proximity point be intruding into it, unless it is related to fixed point. We will see that really it is a concept which is an extension of fixed point, and we will see in particular what are the possible applications, and also what are the possible scopes and motivations behind this development. And again, you can note that developments and applications, I must admit that this is a misnomer. Why? Because in order to catch the developments and applications in a comprehensive way in one lecture is too ambitious a plan. So, what I will do is that I will give the basic ideas, touch upon the ideas, then upon the detailed technicalities, because there are two reasons for that. Because if we go for technicalities, then we will not be able to touch over different areas of development. And the second is that the technical part is related to fixed point methodology, insofar as I will give a treatment to this subject here. There is another direction and another side of the coin in the whole process. I will not go into that. And so, by this time, even if some one of you did not have that much acquaintance with fixed point theory, must have now gained some idea, some I should say some expertise, I should say, in dealing with fixed point methodologies which are applicable. So, let me, it is not moving. This is not moving. Oh, right. So, let me first gratefully acknowledge all the works which form a part of this particular document. Now, what is the program of best proximity? You can see that we have, I think from here it will be better. I was told that it will respond in a better way. Yes, from here the apparatus is actually here. So, what is the basic program? The basic program, as you can see, is the finding the distance between two given sets. So, be sure that we are speaking of distance. So, our implicit assumption is that there must be a concept of distance in the space in which we are going to work. And so, especially when you are dealing with topological spaces where there is not an explicit distance told out, the discussion does not make sense. Most generally, we will work with metric spaces, and at least with spaces where there is some sense of distance that is not really a metric distance, but maybe a generalized matrix distance or like that. So, what is the distance? It is very simple thing that this is the distance. How do you define it? Take x out of A and y out of B, make an infimum of them, then you can be sure that this is DAB. Now, the point is that by taking the infimum, you do not commit yourself that there are actually 2 points between which the distance is actually the minimum distance, because infimum may not be attained. So, you cannot say that these 2 points, if I can find, I will have a distance. No, you cannot say. And that is the concept of best proximity pair. What is a best proximity pair? If you are fortunate enough, I tell you, if you are fortunate enough, because this is not automatic, that there is one point x and the other is the one point y star, such that dx star y star is equal to distance of AB, then we say that this is the best proximity pair. Then our two questions will come up. How to find them if they exist at all? They may not exist, the infimum may not be attained. And second thing is that in the present context, how they are related to fixed point theory. These are the two immediate questions. Before going into any technical discussion, we must give a framework in which we are going to discuss the whole thing, and for which these two questions must be answered. So, there are many ways of doing it. The way we will adopt here, before that you can see that if it is a set A and if it is a set B, two parallel lines say. So, best proximity pairs can be an infinite in number. X star y star is a best proximity point. You can see P star Q star is also a best proximity point. So, there is nothing to assume to the effect that whenever such best proximity pairs are in existence, they are going to be unique. So, uniqueness, even if they exist, uniqueness is not automatic. This is a very simple consideration which shows you. But actual consideration in mathematics arises in those spaces where you lose the contact of visuality. What you are doing is something with a subset of 2 dimensions. At best, you can have a construction in 3 dimensions. But do you have a construction of more than 3 dimensions? And sometimes dimensions do speak. What is true in R4 is miserably not true, rather which is true in R3 is miserably not true in R4, and vice versa. And the second thing is that you do not have the concept of dimension in many spaces, and actually in metric spaces we do not ask for dimensions, and we are having a general discussion on that. So, things are not so obvious in abstract spaces. Now come, how can we have that? Can the non-self maps help in any way? Suppose A is a set and B is a set, and ideally we assume that they are separated, that is, there is no meeting point of them. So, we consider T from A to B a self map. So, T from A to B is a self map, and if it so happens that there is a point x star which under T is being mapped to T x star with this particular things happening simultaneously, that d x star y star then becomes infimum of dAb, A belonging to A, B belonging to B, which is precisely the distance between two sets. Then we say that this point is a best proximity point of the function T, with the help of which, or by which, I must say that the minimum distance between two sets A and B is attained, and it solves your problem. Now, question is that whether such a mapping can be constructed, and if constructed, how? And the second thing is that if we are given an arbitrary mapping, is it possible to ask and answer the question that whether such a mapping will, such a point will be there which serves this purpose? Now look at it. If you have one point z from here and the other point tz from here under the mapping T, then you can see that ztz is greater than equal to dAb, obviously because this is the minimum distance. And so when you have that thing, the problem is to minimize ztz. But in minimization, there is no guarantee that it will be minimized to yield such a point x star such that this is going to happen. If in the process of minimization, you can assure by imposing some sufficient conditions that the other thing is going to happen, then you can say that we have attained a best proximity point in this particular case. Sure. So, it gives you an idea that essentially this is an optimization problem. Not only that, it is not local in nature, it is going to be global optimization problem, because you will have to minimize it over all z belonging to the domain, and this makes it into a global optimization problem. Don't be just misguided, I say misguided by the deceptive simplicity of this particular picture, because these sets may be abstractly very, very complicated in appropriate spaces, and the problem becomes really non-trivial. How it is related to fixed point? Yes. This we have spoken, and it should be, the problem should be distinguished from best approximation results. I will come to it, because there is a famous theorem due to Kaifan, and Kaifan's theorem, if we look into the early literature of the best proximity point, this is not very early because it was initiated in the middle of, I believe it is in 2006 in one paper by Eldred Biromani, and possibly also authored by Kirk at the same time. It was the first result. Anyway, I will come to it. So, how it is related to fixed point? Look at it. Now, suppose dAb is equal to 0 here. What happens? That this point x star becomes a Tx star. And when you separate out A to B, then the fixed point vanishes, resembling the bifurcation in, if you are associated with dynamical systems, it is like that almost, but at least in concept. So, in that case, you can see that it is this one is a special case for that. And so, you can see the whole scheme which we are wanting to address can be thought of as an extension of the idea of fixed points. And so fixed point methodology will apply, definitely with some modifications. And this is the relation of fixed point with best proximity point. That is, we can understand it, we can view it. This is one view, but there is other side of the coin, that is the optimization side of the coin. We are not going into it because I am trying to confine my discussion only with that which is related to fixed points only. Then you can see that it is an extension of the idea of fixed point. Whenever DAB is equal to 0, then X star is becoming TX star. And so essentially, as you can realize, that these are actually the situations which are of interest. If it boils down to this one, then we will be doing what we are doing with fixed point, and there is no very speciality in it. There is no point in dealing with it separately as a best proximity point. So our interest will be in this situation, which is characterized by the fact that DA intersection AB is not equal to phi. And so now I say that what actually we do in fixed point, we find a solution of this equation in a fixed point problem. Just x is equal to tx, and then we solve it. If we have a solution, then x star is equal to tx star is that. But if you consider this equation in this context, x is equal to tx, will it have any meaning? Apparently no, but in another sense, yes. It will have a meaning in this sense that we have no exact solution of it. But we can think of an approximate solution even if the exact solution is not there. And this is common in mathematics. This is common when you are going to deal with in mathematical physics in several problems. You can see it. So we adopt that view. That is, we want the approximate solution. Not only that, we want the optimal approximate solution. What is the condition of optimality here? That this approximate solution must be tallying with this one, distance of AB. So the problem is to find optimal approximate solution of a fixed point equation. It is the problem. Now you have a fixed point equation, then there are many methods of approaching for making out the optimal approximate solutions. You can approach with those methods, but we will take a different course now. We will see that we'll combine it with this approach, how a non-self mapping can help us in this respect. Before going into that, I must give you that the Chi-Fan's best approximation theorem, it is like this one. You can say that y belongs to C, and this is actually, we won't discuss in a very, that is, time will not permit, and also scope is not there that way. So this is Brouwer's theorem, and you can see that best approximation theorem is an extension of that. And this Chi-Fan's approximation result, best approximation result, it is known that it shaped the future development of mathematical approximation theory in a fantastic way. Now, if you look into the early literature of best proximity points, then you will almost invariably find in the introduction portion that authors are writing to explicate or to alleviate the doubt that it is not an approximation, best approximation result. What is the crux of the of this sensation, it is that Chi-Pfann's result is not an optimality result, which is the case with proximity point. And it was not Kirk, it was Eldred and Biromani in 2006, Journal of Mathematical Analysis and Applications, made the first appearance of the best proximity point of an operator. Now, when, everyone knows that Chi-Pfann's best approximation theorem that I told, that it had a very overwhelming effect on the future development of approximation theory. Should we expect that our best proximity result is also having that much of influence in the future development process of mathematics also in this field? Incidentally not. It cannot be taken as that much fundamental with this one, but nevertheless, we should recognize it with proper respect in its proper position, because these results are also very important. And now, in last couple of years, we will see that the best proximity results have been applied in a very nice way to yield some I should say, to yield some applications which were not known previously. We'll come to that later. So these are something. This is, as you can see, A0 and B0 are the 2 point sets. These will be very important for us. What is A0? That is, for you take x and you take A, and then dxy is equal to distance of AB. I will go to the board, and you must all agree that nothing is more comfortable than a piece of chalk and a duster for the mathematics people. So this is like this one. This is A and this is B. If you look into it, well, if it is this border is A0 and this border is B0. And then if you have a point here, then you have a corresponding point here. So it is, you can tally with it that this is A0 and B0. Again, I maintain that just trying to visualize this may be dangerous. We should have something, the better we understand, we will understand this situation, the better we have the abstract visualization of the whole thing, just cutting us away from the just geometric visualization. It's my personal opinion, obviously, but definitely the way we geometrically or just have or just pictorially visualize the thing is most important. I also recognize that, otherwise I would not have just drawn this picture actually. So this is the definition that how this is the actually from 2006, the original paper. That is T from A union B to A union B is a mapping. The first part is called the cyclic mapping. TA maps to B and TB maps to A. That means A is mapped to B and B is mapped back to A. If it is the case, then we call it a cyclic mapping. It can be extended, as you can see. In literature, you will find p-cyclic mappings. That means A1 is mapped to A2, then A2 is mapped to A3, and AN is mapped back to A1. In this way, we have a p-cyclic mapping. And then this is the inequality. You can see that 0 less than k less than 1, it is there, and you can see when distance of AB is vanishing, then it is, this part is no more there, and so this is nothing but Banach contraction. Essentially, it is some kind of extension of Banach contraction suited to the context.
Due to Vida Maria Alfred.
Yes, that was there. This was the beginning of the whole thing. And then the construction is like this: xn plus 1 is equal to txn, then dxn txn tends to distance of AB. That is some point to be noted here. Suppose this one is one set and this one is the other set. So we begin with x0, then x1 is equal to tx0. We go here and then go back to x2 is equal to tx1 and then to x3, that is tx2. So what you have here, you generate x2n here and you generate x twice n plus 1 here. If we assume that inequality, then proceed, then this is just what we do with just slight modification of what we do traditionally with in the proofs of Banach contraction, the same thing. You will attain this result. So x twice n in this way will go to certain point and x twice n plus 1 in this way will go to certain point in the limit. It is wrong to say that they will go to certain point in the limit. The main thing is that this one will be satisfied. If they are, we can assure that in the limit they are going to some point, that is they are converging, then you can say that finally we have that when xn tends to x star and txn is equal to xn plus 1 tends to tx star. Sure. So this will come up. And this is, so the most important part is that to ensure when x twice n will converge. And that is not always easy. If x twice n has a convergent subsequence, then to the point to which it will converge is x, which in which case x is equal to tx is equal to distance of AB. This is proved there actually. This will you can prove it with no effort in fact. But when it will converge, this is the great point. There is no automatic mechanism in metric space which will ensure you that this is going to converge. You will have to make very special arrangements. If you want to have something, if you want to work on Banach space, then or Hilbert space, then you have the developed tool of Banach space geometry in your hand. You can apply it and come out with flying colors. This is one of the results. If A and B are non-analytic closed subsets of a non-linear space and finite one span of A or span of B is finite dimensional, then this will happen. But if you say that a span is not finite dimensional, give you an example, this one. You can say this one is this, and B is this one, that is EI is this one, infinite dimensional space. Now you can readily see that the proximity point will not be there, but neither A nor B is finite dimensional. If you go to then, but uniform convexity of the Banach space will give you leverage. If you are working in the context of uniform convexity, then this is automatic, that you will have the required convergence to give you this result. So in Banach space, and particularly in Hilbert space, this will be automatic. So what was there in that, and what we have used? Just the ideas of the geometry. That is most important. And so you look back again. Let us look back. We are using here, not really here. Yes. This is, what is this? This one is a Banach contraction here, and an extension of Banach contraction in the sense that we are talking of here. So now, more than 100 years have passed since this Banach contraction was first given. And if it will not be, I will not deviate from truth if I say that hundreds of generalizations of Banach's contraction have come up. Can we use these contractions, or at least some of these contractions, for this particular purpose? Why not? I will show you one result. So let me give you one particular. This is a particular function, empty function. It is given like this one. I will not really elaborate over it because it limits supremum of something, and etc., etc. This is the requirement of it. If you are if you have some interest or have some study of fixed point theory, you will be knowing what empty function is. Now, how empty function is used and what is its relevance? You can see that we are going for the multi-valued one. What is the distance between two sets? The distance between two sets can be understood in very different ways. So one of the established ways of looking into the thing is to use Hausdorff distance, that is HAB. Think of this one. What is that if I want to see it in this way? Again a picture which I discouraged. And then you take this distance and take this distance. So this distance you take alpha and you take distance beta. You take maximum of alpha and beta. This is the distance between two sets. Assume that they are closed and bounded. And now, if you juxtapose it, just A equal to B, that is, you are just putting A over B. Then what happens? These two things will just shrink to 0. Then what will be coming up? For A equal to B, this HAB is going to be equal to 0. And it is if and only if condition. Insofar as you are maintaining it as closed and bounded or at least compact. And HA is equal to, by symmetry of the definition, HB is equal to HA. And again, you can see that, yes, triangular inequality will also hold. You will have to be analytical to see that triangular inequality will hold for this particular definition. So this is the concept of Hausdorff distance. With this at hand, we have a nice generalization by Nadler of this theorem of Banach. And this is actually through this result that the study of contraction mapping enters into the domain of set-valued analysis. This is a very famous and very influential result. And after, you can see that HAB, if you treated them as singleton sets, this is nothing but the Banach contraction. Then you can have another generalization of it. That is, if you have mu is equal to this one, don't put just a multiplicative constant here, but replace it with a function which is of this character, the empty function, whose character is just this one. Then amazingly this has a fixed point. Oh, you must, I must define, which I have not defined, that yes, this is x is equal to t, x is a fixed point, no doubt about it. But if you have a multi-valued mapping, then what happens? It is taken not to a point, but now Tx is a set. In that case, we have an extension of this idea to the multi-valued case when x is belongs to Tx. You must be knowing through these lectures. It is a duplication on my part, I suppose. Anyway, now this is a part of a long, I should say, effort for generalization of Banach's contraction. Now, when you have a Banach's contraction like this, d Tx Ty is less than equal to k into dxy. So this is a constant. Next question comes. This is a logical question to be asked historically. That is, can I replace the constant k by another function? If k is equal to 1, then everyone knows it becomes a non-expansive type of mapping, and it's not easy to find a fixed point of that under ordinary conditions. There are volumes written on fixed points of non-expansive mappings, and you will need to have very special conditions in order to ensure that such fixed conditions is there. By its own merit, it is itself a subject of mathematics, the fixed point theory of non-expansive expansions. Am I correct? That is, so another direction is that why constant? Why not a function of dxy? First response came from Boyd and Wong. They gave one function, putting it in place of k will be giving you the fixed point. And now, can we, yes?
Why it is the function of dxy? Because dxy is also a number. Why it cannot be a function of x and y?
Actually, k is a number. We are wanting finally to have a number, but that varies with x and y in that way. So it is finally it's a function of x and y. So you'll have to start again. Function of x and y. तो दी जनरेटर चालू हो जाएगा. Yes, it has come. Oh, yes. Yes, yes, it is visible. Visible है. बड़ा होना चाहिए. Full screen. So we were interrupted. Anyway, हाँ 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 इसको बंद कर हाँ sure. So this is the empty function. Now, with that thing at hand, you can see that this was the further generalization of Nadler using empty function. That is, one of the authors is Takahashi, famous mathematician. Now it was in 1989, you can see it has a far-reaching consequence on the contractive fixed point theory. Yes. It has a far-reaching consequence. So can we not use this function in place of our Banach contraction directly into our results? Answer is in the affirmation, and this one is that result, as you can see. Yes, our empty function can also be utilized that way. So when empty function could be utilized, and further you can see there is an application of empty function in this case also. Empty cyclic Siric type contraction. If it is like that, it is nothing that you have mxy, you can see it is not dxy but maximum of this expression. And then put the empty function on it, that mu or phi on it. And then now you have this result. And if you can just use this result as you have used in the original paper of L11 and Biramani, you will find that it also yields a proximity point result, best proximity point result. And incidentally, this result was proved in 2024, and a remarkable one. It has in its proof a methodology which takes into account something else and avoids using the certain concepts of Banach space geometry. And this is the speciality of the whole thing. And with this result, I will give you how it is applied. This is a locally compact group, and then it is proved. I will not go directly into the group. Then if it is a locally compact group and key from G to G from R, then this equation has a unique solution in the context of group. So these are the applications even which could be derived. So next comes the P property. Now what we were discussing is a bit restrictive. What is the restriction? That we were doing with this type of situation, that here is A and here is B, T is mapping from A to B, and then whole B is mapped into A. This is B, and B is also mapped into A. So this is like going cyclic. Is it possible? In our original way of thinking, we did not assume that cyclicity of the mappings are necessary types of things. We started with these types of non-self mappings down there. And what is then the methodology should be changed now? What is the change in methodology? That is again borrowing in some ad hoc manner the property which is called this P property. As you can see that when y1 is equal to z1, y2 is equal to z2, then this is the property. Then this is y1, z1, this is one proximity pair suppose, and y2 is equal to z2. This is naturally a0 and b0 of the whole space. This is a and supposedly this is b. If it so happens these two are both are equal to DAB, then these two lengths are equal. This is called the P property. It has weaker versions in the literature. I will not go into that much details. And when weak property, P property is satisfied closed interval AB? This is one. AB are non-empty bounded closed and convex subsets of a uniformly convex Banach space X. It is automatically satisfied. And second thing, another example is this is the modified P property or like that. So as you can see, when you are going to use this P property, then what is automatically satisfied in a uniformly convex Banach space or in Hilbert space, you are just borrowing in an, I should say, the borrowing of idea, not the borrowing of the technicalities in one sense, but in an ad hoc manner from those structures into your metric space, because you need to borrow, because in your metric space you have nothing, no structure. Only when you come to the cat spaces or like that, then you have the comparison triangles or like that, you can take up what you see actually into those spaces. That is a separate study, I will come to that. So with this P property assumed, then you can have results again on this. You can see this is one way, multi-valued. I have taken multi-valued, you can, as a simple case, take it as a single valued. So this is Adler in 2000, I believe, in 2012 it is. And as you can see that the subject has not completed its two decades of existence. So there is a, this is an example for that. And this is multi-valued non-expansive. It also has certain, on Banach space, if you impose certain conditions, then it will also give you the best proximity point. I have omitted, then there are also in 2022 a nice result has been published, and which has applications again to homotopy types of things. And this is again, I have repeated. Let us go back this way, and this is the result. I think I should, how much time I am having now? 20 minutes. 12:45, right, 25 minutes, 25 minutes, 25 minutes, okay. So this is common best proximity point. This is again another problem. When we speak of fixed points, then a topic very naturally comes, what is the common fixed point? So why not talk about common best proximity point? Can there be results on best proximity point? Yes, there can also be results in this way. This is common best proximity point result. As you can see, these results are also available in literature. Now comes that you see, I think Professor Imdad will be speaking in the next session. So, and he is going to be relational fixed point theory. So we will, myself will also be in the audience, because it is the expertise of Professor Imdad that he has done quite a commendable job for the fixed point community. The main idea is that if we are looking into the traditional proofs of Banach contraction mapping theorem, dTxty is equal to less than equal to k into dxy. We assume it for all xy. there is no need to assume it for all xy. Because in your, if you look into the traditional proofs of that, then you begin with x0, then tx0 is equal to x1, tx1 is equal to x2. What you do is do it on this particular sequence, which is actually called the orbit of x0, to be formal. And now in the whole process, you need to mainly you need to apply this inequality only on the sequence, on one sequence which is obtained in this way. The other parts are not that much required. So you can just avoid those things. You can just make them redundant and just maintain that yes, my inequality needs to be satisfied only on certain subsets of x cross x. What is a subset of x cross x? R is a subset of x cross x. Whenever xy is belonging to R, then I say that these or these other types of inequalities, not necessarily this one, is satisfied, maybe my condition, and this is the, I should search for a minimality of the R so that it is sufficient for me to give you the final result. Still, R sometimes will require a structure. What can be the structure? R is like, you can see this is a relation. What can be the structure? One structure is graph. Yes, एसছে আসেনি, it has not yet come, अभी तक नहीं आया. इसको ऑन करना पड़ेगा, अभी तक नहीं आया. But as I was when I finished, that R may require some very special properties. So one of those is graph, that, and particularly here we have taken the directed graph, because you will have to have a mapping from A to B, right, x star to t x star, not from y star here to t y star. No, I will have a one-way flow and one-way traffic, and for that purpose we have, this is constructed, it's not our work. So this is a directed graph, and with the concept idea of directed graph imposed on the metric space, we have a combination of two types of methodologies. One is the graph theoretic methodology and the other is metric or analytic methodology. So one is order theoretic, the other is analytic. We can blend them and see that the results are obtained. And actually results are actually obtained, you can see. So I skip the details of that. So sometimes we call it a G proximity point. It was the result published in 2023, quite recent result. And as someone was asking me in the time of just in between, that what can be the directions which can be taken up. So this is one direction in which proximity point theorems have not advanced in a very large way. One can take up and combine it with the metric space by imposing some additional structure, see how these results, new results can be obtained. And now, these are the results I will definitely, and this is the one that is the measure of non-compactness. It also just plays a very large role in the whole process, and Professor Javid has proved certain results on proximity point using measure of non-compactness. These are the results. I should skip the details and should maintain that with Caputo derivative, the fractional differential equation they have considered under certain conditions, it has been proved that it has an optimal solution under certain conditions. I have not given the solutions. It is a very interesting application. Why interesting application? The application is interesting because the solution, sometimes what we do, sometimes we seek a solution, there exists a solution or like that, of some differential or integral systems are like that. This is a very, as we have learned from Professor Bohuguna's lecture, that this is a very, I should say, very interesting and very useful method of mathematics, particularly of applied mathematics. And now the thing is that there may be certain systems which does not admit of, or there is no guarantee that it will admit of solution. Then what should we do? We should go for the optimal solution. Optimal in what sense? There is no definite benchmark. We need to define optimal according to our needs. Your need for doing that thing, what you need for optimality may not be coinciding with me. So this is something optimal with respect to what? This is a very great question, and you will have to set the problem in that way and then obtain the result. And this is one of the examples in which it has been done, and I think this approach will be, I don't say this is this technical approach, I say it is the approach. The approach of idea may be very useful in different areas. I will touch upon this one. This application is in chaos solitons factors. This is some Altun and etc. in 2021 they have published. Now, what we know is that fractal. What is a fractal? Everyone knows what is a fractal, and mathematically if you want to see it, then fractals are self-similar sets. That means There are many fractals. One of the very most common fractal is your Cantor set. That means these are the types. You can repeat this process. This is not a fractal in the mathematical sense. This is a fractal which you can, after certain iterations, you can have this figure, but if you go on doing it, then in the limit you have certain sets which are called fractals in the mathematical sense. And arguing in the mathematical way and in the way the argument is taken in computational science, rather particularly in computer science, are not one and the same. You will see in papers of computer science, these are called fractals. But if from mathematics one question comes that where is the limit? You have done 50, 500, 5 crore, 50 crore iterations, but you have ultimately stopped. Where is the limit? So the limit is always, this is the basic difference in the two approaches. That is, xn tends to x. This means mathematically very certain. Xn is equal to yn for all n. This means that the two sequences are one and the same. But from the computational point of view, this means xn is equal to yn insofar this can be asserted. That means it depends on your power of computation. So these two approaches, if not contradictory, are not one and the same. So anyway, with that at hand, let us look into it. So there is a self-similarity. In a very restrictive sense, you can do that. If you want to see the self-similarity in it, you will have to commit yourself to the group with finite generators if you want to be mathematical. But if you can, in some limiting process, push it to a transformation group with infinite generations, then only in the mathematical sense you have a self-similar type of thing which can be described as a as a fractal. Anyway, for our purpose, this is the Hutchinson-Barnsley operator. That is, we have contractions, and now we don't require them to be contractions. These may be generalizations of the contractions even. And then you have this operator fa union from 1 to n fai. Ai's are collected from kax, that is, these are compact sets. So the place of abode for fractals are compact sets. This is not my terminology. I am borrowing it from some very highly cited paper that this is the place of abode for the fractals. And if you look into this equation and see that there is a point C when Fc is equal to C, what happens? Just forget something in between. Everything is changing with Fi, but when you are applying f on A, the intermediate things are not visible. Got my point? I think that I have a circle like this. This is F1, it rotates, F2 it rotates, F3 rotates in the reverse direction by pi, 3 pi, and then 2 plus 1 pi, anyway, whatever be it. But if I look into the circle, just disinterested with a disinterest in the fact that what has happened with the particular Fi's, then I will see that the circle has not changed. I will see that there is a self-similarity in the whole thing if my viewing is through F. This is actually the crux of the Hutchinson-Barnsley theory, and in this way, this is a very famous theory for generating fractals, HB theory, and has many, many applications actually. Now the point is that if we can, we have the, and for that purpose we call it, this is called, I have not written it, anyway, it is written later. We have an extension of it. Yes. Let me give you the result. Now, everyone, it is known that, let me again go to the board, H is the Hausdorff, let me use the small h, it has been used as small h. Small h is the Hausdorff distance. Now, A and B are two compact sets. In this way, if we begin with XD as a metric space, then K is the set of all compact sets and H is the Hausdorff metric, then this is also a complete metric space whenever XD is a metric space, a standard result. And now from that construction you can see F is a mapping from Kx to Kx. Instead of Kx, if I take A and if I M and if I take N, these are subsets of Kx. Mind it, very important to note that elements of M are compact sets. Elements of M are compact sets. So, distance between M and N, what is that? Should be the Hausdorff terms of Hausdorff distance, that is minimum or infimum of HAB. A belongs to Ka and B belongs to Kb. We call it here, for notational purposes, let us forget the previous notations, HAB. We call it. I mean, subset, we are taking subsets, not that, sorry for that. So, we call it is equal to HMN. If we construct this one as the function f as this one, such that this one is satisfied, then we have a unique best proximity attractor. It is a generalization of the previous theorem. Here we deal with what is called iterated function systems. This is called iterated function system known as IFS, very special name and very famous name. Then here we will have PIFS, that is proximal iterated function system. What does it generate? If we go into the numerical study, this is, you see that this is R. That means 1 by 8 radius. With 1 by 8 radius, you take a circle. This one is this. And you have F1 this one and F2 is this one. With this, you construct the PIFS, and what is the fractal generated? You can, as I told you, that this is the approach of the computer science. You will have to stop somewhere. But in the whole process, you can see that yes, some pattern is being generated. This is the two-dimensional Cantor set, as you can see. If you suppress one dimension, you can see the 1/3 Cantor set is coming up. Just suppress the two dimension into one, your familiar Cantor set. Two-dimensional Cantor set is generated. And this is generated by PIFS, a very separate way of generation from the previous one. This is a marked improvement. I cannot give you the details of it because it requires a little more elaborate discussion, but this is a marked improvement. And as you can see, it appeared only in 2021, and you can see that it has been further, in furtherance of it, some results have come, not too many results yet. This is another direction in which the young researchers can proceed with the proximity point theorems. I was being asked by several of the young researchers, so I am telling this particular point very specially. Oh, my time, Javid will not allow me more time, I know. So just, I will not.
7 minutes, 8 minutes.
Okay. So I will be, that is the coupled fixed point. What is a coupled fixed point? You can see fx is equal to, fxy is equal to x, fyx is equal to y. This had a controversy actually, and some coupled fixed points it was given that these are nothing new, only the fixed points on product spaces or like that, but there was also a counter argument for that. So, viewing something from another point of view does not nullify the first point of view. This is also the fact. Anyway, so we are not going into that, but beyond this thing, because this controversy will not just touch us if we are going to have the contraction like this one. This was the famous work of Bhaskar, 2006 again. Yes. So, this is the actually the, and we could, this is the coupling actually, coupled best proximity point, and it is the coupling. What it is the coupling, I will give you the idea. This coupling has been utilized in working out the generation of fractals already. You can find the paper, I think 2022 or like that, in chaos solitons fractals. You can find the paper. And coupling has also been utilized in other contexts as well. So, this is like this one, that you have AB, from here you take x, and from here you take y. So, you make fxy, it will plunge you here. And if you take fyx, then it will just move you here. So, this is the coupling, that one is coupling and it is moving it, the product of the whole space is moved to one space, and the other way is also there. In this way, we can have also what is the gain in it. As you can see, that we require these two equations to be satisfied, and this is one way of attaining DAB, and you can see this is other way of attaining DAB, because neither x is y nor fxy is equal to fyx. This is the difference. These are the two different pairs, and by a single theorem or by a single algorithm, you can just derive or have in your hands two pairs which serve your purpose simultaneously. This is the importance of coupling, and it is possible. We can give you the result how. This is an example for the result. This was in 2018. This is, as you can see, by mimicking the result of L11 and Biramani, this could be done for the coupling, and that too for multivalued coupling. But we have used delta distance, not h, in this particular case. So, I should not proceed any further, but I will give you some. Already we have mentioned that fractal generation by proximity IFS, proximal IFS, is a good candidate for taking up research. Then construction of algorithms for proximity points. You can see that we have many, in fact, it is called the constructive fixed point theory, that we have different algorithms, fixed point iteration sometimes called, that is starting with Mann iteration, that is one step, then Ishikawa iteration, three-step iteration, Noor iteration, it's many types of iterations we have. What is the utility of it? Because whenever, in many cases you see that we prove that such an integral equation has a solution. How do I prove it? We quote some, if we are going to utilize the fixed point theorems, then we quote some fixed point theorem and then satisfy it in the context of our integral or differential equation, and then conclude that it is satisfied, so it must be having a solution. So, the question that it requires to find a fixed point is bypassed. Just a fixed point is there is sufficient for us. No, this is not the case. I will give you just one example. Suppose we are doing with everyone knows if we have a three-dimensional sphere, suppose, and in this three-dimensional sphere, let it be filled with water or any fluid, whatever be it. And then T from three-dimensional sphere D3 to D3, filled with water, a particular continuous function. And from Bauer's theorem, what we have? There is a point Z is equal to Tz. Got it? It's a very well-known fact. But how do I realize it here? If you go to fluid dynamics, tell some, that is applied physicist or applied mechanics people, just construct such a table which realizes this one. What they will do is that they will make the arrangement of a pipe this way. That is, fluid is taken out and infused. Got it? And how do you know that this is a continuous transformation? Very simple. Go to the fluid dynamics equations. If it is a perfect fluid, then solve the Bernoulli's equation. If it is a viscous fluid, then go for Navier-Stokes equation. It will give you a continuous path, and then the capillary flow, and then just squeeze it. It will give you, and again, no experiment on earth is ever perfect reflecting the mathematical idea, not even in the atomic and subatomic domains. There is a gap. Here also, you cannot make a pipe into a line. This is fact, but you can make it approximately to the desired degree of approximation insofar as it will not contradict the Heisenberg's uncertainty principle, whatever be it. So it is infused from here to here. And here is the point Z is carried to Tz. This point is Z1 sucked out and placed here to Tz1. So there is a strong topsy-turvy of the fluid. This is called the turbulence of the fluid, a very technical name. If you are a student of fluid dynamics, you know that this phenomenon is called a turbulence. It's a chaotic phenomenon. And in the whole process, there will be a point Z bar is equal to Tz bar. If you are here, you will be just thrown out here. But if you are at Z bar, then you are safe. But you are safe only when you know Z bar. And that is the reason that you need to know Z bar. And that is the reason that you need to construct algorithms and iterations, whatever you say, which takes you to Z bar. That is the justification of that from the applied point of view. And now this also applies to, if you justify it for fixed points, why don't you justify it for the extended concept of proximity points? There is an interesting whole thing in it. Now proximity points involve two sets. Although subset of a same set, they can have very different characters. If you are doing with one Banach space, then yn plus 1 is equal to xn alpha n xn plus 1 minus alpha n, then t xn. It makes sense. But here it may not make sense. They can have very, very different characters. So their construction is not going to be very easy. And this is very interesting type of problem which has a very vast domain of unexplored vast domain, I say. And so this can be taken up. And lastly, I must say that one is that the proximity point problem in cat spaces. Here, what are cat spaces? That the time is very scanty, that it is that there are comparison triangles, and with the help of that we invite geometry into that space. So geometry of the reals R3, R4 or like that. Now professor has done a very good work which has come to our notice, that you have taken the comparison triangles in LP space in one of your works, and we really appreciated this work, and we felt that it is going to just give us an opportunity to work in more general setting. And so here also the proximity point can be studied, and I think if you particularly in Carpathian Journal of Mathematics in 2024 one particular paper has already been there, and so it can be taken up for consideration. And lastly, I must say about one thing, that random version of proximity point studies. Why we require randomness? Suppose some of you have definitely read Shakespeare, and particularly the Macbeth, it's not Macbeth, it's Hamlet. There, Hamlet affected madness, and some person, they were commenting like that, there are methods in his madness. So if you look into the sky, just look into how the clouds just conglomerate and then they disperse, they scatter around. You will see that nature is exhibiting madness, but there are methods in this madness. And whenever there are methods, there are regularities which can be caught in the language of mathematics. And what we do is that we have the mathematics to deal with random phenomena. We require for our, in addition to our differential equations, we require a random element infused in the differential equation. So it becomes a random differential equation. And again, in this random differential equation, when you are going to solve the differential equation or give at least the existence of solutions by using fixed points, for that random part what you will do. And random differential equation is not a very recent development. This was, I believe, in 1972, A.T. Barucharid. It was his work, random integral equation, all the same as differential equation. And again, Segal and Barucharid, their famous work on random fixed point. So you require a random version of these fixed points. And when you require a random version of the fixed point, then why not go for random version of the proximity points? This is also a good problem and will serve many of your purposes. There is another point, which I will end, that for the purpose of uncertainty coming out of the random nature of things underlying, there is another way of doing, that is the stochastic way. Sometimes random and stochastic, I have seen papers written as stochastic fixed point theory dealing with random fixed points. But when you go into the stochastic differential equation, the story is very different. You don't use these types of integrals. You have Ito's integral, Stratonovich integral, you have martingale, and etc., all types of things. And in that domain also, the fixed point study is there and important, and also in that domain, I believe, although I feel that not much has been done, I have not come across any such paper, at least now, but I believe that in that domain, stochastic proximity point problems can also be taken up with, and it is mathematically profitable, I believe, that these things can be done successfully, and I think will be giving good leverage in our theory and applications both ways. So let me end here, and these are our, as I promised you that I have not gone very deeply into the technical studies, because technical studies are quite elaborate. It would have restricted what I wanted to say, but I dwelled upon the ideas only.
So, any doubt, any question you can ask Professor
I
Vinay.
want you to go back to the fractals.
Fractals, right? Yes.
close to the muscle.
Close to that one, yes. Close to. Yes. This one is the fractal generation. Back.
Regular fractals.
Regular fractals, yes. This one.
No, these are.
No, this is proximal. This is.
But,
This is.
Forward.
forward.